Yeah, next team, please. We can start with a new presentation. Fourth one, right? Faster than the propeller aircraft for range and endurance. Ensure that irrespective of what content you have already prepared, your focus is essentially getting towards answering that question by the end of your talk.
Good afternoon, sir. Good afternoon, everyone. So, our topic for today is why jet aircrafts fly at a higher altitude with a higher range and endurance than propeller aircrafts. And our subtopic is basically how the propulsion system affects this criteria for these two different aircrafts. So, as you can see over here, this is the propeller ceiling at around 28,000 feet. Above this, propeller aircrafts can't fly. And for jet aircrafts, they can easily cruise at 45K. So it is a we want to know why this performance gap comes between these two different kind of aircrafts. As you can see over here, the same central question. So first, our first theory that we want to explore into this is momentum theory. That basically we know that the thrust is basically mass flow rate multiplied by change in velocity, right? So how does a propeller engine and how does a jet engine differ in this particular use of this equation? So if you look at it, what propeller engine does is takes a high mass flow rate and the incremental velocity is very low. Whereas in case of jet engine, the mass flow rate is low, but the incremental velocity is very high. So as you can see over here, the propeller gets a large volume of air, but it accelerates very slowly. So they both try to magnify one aspect of this particular equation. And second thing is propulsive efficiency. As we know, propulsive efficiency, if we derive the formula, it is 2V upon V plus VE. So according to this, our propulsive efficiency will be maximum when our exhaust velocity is equal to our flight velocity, right? So as you can see over here, that is theoretically impossible. As you can see over here, as we go higher in flight velocity, for a propeller it drops. The propulsive efficiency completely drops. So as we for that is the reason we can't use a propeller because it is so inefficient at higher velocities. Whereas for a jet aircraft with flight speed, the efficiency improves. Then the second thing is power limited constraints. So as you can see over here, for a propeller aircraft, the thrust is basically a function of power. It's power multiplied by the efficiency divided by the velocity. And as our speed increases, the thrust available will decrease and the drag will increase. So after this point, we can't actually use the propeller aircraft because our drag will be more than our thrust. It is inoperable. Now I will discuss the basic working principles of these two engines. So this is a turboprop engine. As you can see over there, there's the propeller fan, and this is the engine. This is basically a gas turbine engine, where the fuel is combusted in order to produce mechanical energy to run this shaft, so that that propeller can run at a higher at a particular RPM in order to generate thrust. This is like there are key features. It's gas turbine, exact maximum shaft power, and simple. It is like typical output is around 1200 to 3000 kilowatts, and TSFC is around 0.3 kilogram per kilowatt hour. Optimal speed is around 550 kilometers per hour, and ceiling will be around 9000 meter. It can't go above that. That is 30,000 feet. As you can see over here, here's the altitude performance of the same turboprop engine. Is the thrust, and with altitude, the thrust is decreasing, and basically TSFC, there's a minor improvement in TSFC, but the thrust decrease is very high. So this is the practical ceiling where we can run this particular engine. Whereas let us look at jet engine, how jet engine works. Basically, jet engine, this is a turbofan engine. It's kind of jet engine. Turbofan with a bypass ratio of 9:1. Only one volume of air, 1 out of 10 volume of air will go inside the actual engine. It will then go through a compressor, then it will combustion chamber, then it will go to a turbine, then expand it to the nozzle, and where it will mix with all this remaining air, and this will produce the total thrust. As you can see over here, with altitude, how thrust is varying for a propeller engine, and this is total true airspeed. It improves with altitude, and this is TSFC, it's reducing. Then what is the advantage of jets and propeller? So the jet engine, the way it is designed is the thrust is a thrust system. Basically, the thrust for a jet aircraft is constant regardless of the velocity. Like in the initial, except for the initial phases, once it goes in that particular range, it will be constant. So the power available will continuously increase with the velocity. Whereas for a propeller aircraft, wait a minute. Uh, yeah, for a propeller aircraft, it will decrease. That's it. This is like, as you can see over here, it is a comparison between propeller and thrust. So as you can see over here, for this particular region, for this particular regions of velocity, we have this excess power for thrust for a jet engine, which we can use for climb. And after that particular line, this is the line where this drag actually intersects. So we can't operate in after that because drag will be more than thrust. This atmospheric envelope, as you can see over here, how temperature changes in the atmosphere. As we can see, it decreases. After that, it becomes constant. Oh, this is density. It decreases in. This is density, and this is temperature. Blue line is temperature. That is density. Density decreases, where temperature will go up to tropopause. After that, it will be isothermal layer will start. So as we move in higher altitude, we know that temperature decreases and density as well decreases. This is what it shows, and how this will help us. As we can see here, the way the engine is designed, actually it is completely dependent on density for the propeller engine, and because of that, as increase in altitude happens, our density decreases, the mass flow rate will decrease, and so does engine will not be able to work. Whereas jet engine is not completely dependent on density because the design will have the even though density is lower, the high velocity air will ram into this particular section of there, and because of that, it will increase the total pressure. Because of that, recovering that total pressure, it will be able to compensate for low density. And that is the reason mass flow rate would not be affected. Then the same thing, ram pressure recovery, how dynamic compression in front of in front of a jet engine will allow us to convert that kinetic energy into pressure. And this artificially increases density at a compressor phase. Even the atmosphere is thin, as you will see. This is the same thing, how propeller engine will starve after a particular altitude. Whereas for jet engine, because of the ram recovery, even though at a higher Mach number, it will still have a very high pressure recovery. So there's the second requirement is like, as we know with altitude, our velocity is a function of lift. Of lift is a function of velocity, and that directly comes into this equation for when we want to find velocity that we want to fly at a particular altitude. So we know that for flying at higher altitude, we basically need more velocity. So velocity and altitude are not independent of each other. For flying at higher altitude, we'll need higher velocity. So that is the reason. This is what this graph shows. So even though density decreases, but as we go ahead in altitude, we increase the altitude, we have to increase the velocity of our aircraft. And for this reason, propeller can never work in this particular region because it won't be able to produce that much velocity. That's it. So how thrust for a propeller aircraft will collapse at a higher altitude. So this is thrust available from propeller with altitude. First we saw with velocity. As you can see over here, after this particular 30,000 feet, it will just collapse completely. And it has compressibility limits as well at this particular location. This specific fuel consumption, how it is defined in propeller and thrust. And this is the another advantage of the jet aircraft. So what will happen as we reduce the temperature, this will allow us, since our T ambient is lower, our efficiency will increase. So our work output, which was originally this much, because of lower temperature of the ambient air, it actually increases. So our total work area, it increases with higher altitudes. That is the reason jet engines are even more efficient at higher altitude. because the efficiency will increase. And the second thing is specific fuel consumption will decrease as well. Then this thing is drag minimization. As you can see over, this is a propeller curve and a jet curve, and they both find their like minimum drag at different velocities. So for jet, it will be a very as jet after a certain for a propeller aircraft, after a certain velocity, drag will increase exponentially. For jet aircraft, it is basically delayed for a certain range of velocity. So this is basically a range equation, as you can see over here. This is the range equation for a jet aircraft, and this is one for propeller aircraft. As you see over here, for jet aircraft, increase in altitude basically means higher velocity and lower TSFC. So basically, higher altitude will give us more range for a jet aircraft. Whereas for a propeller aircraft, increase in altitude means lower efficiency, right? That is the reason as we go higher, our range will decrease for a propeller aircraft. So as you can see over there, it is the specific range plotted against the velocity. And see, propeller will peak and it will just go down after for a certain velocity, whereas jet will have its peak at a very high velocity. So the second thing is we want to look at endurance. What is how we can maximize endurance for a jet and propeller? For a propeller aircraft, it is a power limited system. So endurance will be the minimum power required, which will be happen at CL to the power 3 by 2 divided by CT max. Whereas for a jet aircraft, it will happen at L by D max, right? And that is how we design for if we want to maximize endurance. So propeller will give it endurance at minimum power, and jet will give us at minimum thrust. Then the second one thing we need to look at one other thing is basically critical Mach number. Since we know that propeller aircraft has this big fans, the blade on this fans, the tip can actually achieve a velocity higher than the speed of sound, and that will result in shock formation, which will be very bad because if shock waves are formed on the propeller tip, it will basically the thrust will collapse completely. As you can see over here, how the drag will rise as soon as we reach that region. As you can see, drag divergence for a propeller aircraft with a straight wing, and drag divergence for a jet aircraft with a swept wing. So as you can see over here, jet aircraft allows it to fly at a higher speed. Same thing. Other thing, in a way, we delay drag divergence is by using swept wings. So whenever we are designing jet aircraft, we basically use swept wings, which reduces our effective Mach number, and that can allow us to actually travel for further for even higher velocity, and without shock waves forming on the wing. This is the same thing. It is I'm trying to show here is what is the ceiling for a propeller aircraft and jet aircraft, and this is the stall speed and the critical Mach number. So for a propeller aircraft, this will be the ceiling altitude. For a jet aircraft, it can go until the coffin's corner. So this is how basically is the overview. What are the things that will impact a propeller aircraft? So air density, it will reduce the thrust. Flight speed will reduce as well. Blade pitch can come into it. Temperature and compressibility factors. And this is factors affecting jet engines. Of course, flight Mach number, but inlet pressure will rise because of that. Bypass ratio will help us to achieve a more having higher fuel efficiency. Then compressibility we can avoid until 0.9, Mach number less than 0.9, and ambient temperature will give us better efficiency. So altitude basically, our conclusion is that altitude basically favor jet aircrafts, jet engines in general. This is the performance difference between jet and propellers. Now I'll ask Deep.
Good afternoon, everyone. So, as here already given all the parameters affecting jet and propeller engines, so I will continue with the various examples, design examples which are present. So these are the research validations. So so these are the figures for the turboprop as well as the jet engine. So turboprops, as he has said, has a lower cruise altitude and a speed and lower airspeed as compared to jet aircraft. Also, because of the Breguet equation, so jets achieve 4x the range at twice x the altitude, and also they have lower TSFC. So that's why you get 4x the altitude at higher altitudes, 4x the range because of higher altitudes. So these are the various propeller designs. So we have Cessna, King Air, and the C-130H. Cessna is piston prop, while the other two are turboprop. In case of piston prop, what happens is that it's not like a normal car engine, which drives the propeller instead of the jet, which actually drives the piston and then the propeller. So turboprops, as we can see from the cruise speed and the cruise altitude, are more efficient as compared to piston props. And this is for the jet engines. So the aircraft are Boeing and Gulfstream in this case. So as I had already said, because of speed and because of altitude and lower TSFC, jets tend to have higher endurance. So these are the two examples which we are presenting here. So this is the performance envelope for C-130, which is a turboprop engine. So as you can see from the graph, it operates at a lower altitude and has a density limit, because as we go higher, the density decreases and it can't go fast enough. And also it has a speed limit also because of the tip Mach limit, the critical Mach limit which we have. And this is the performance envelope for a jet in this case. So in this case, as you can see, the speed is more on the higher side here, while the altitude also goes towards the higher side. So higher altitude helps the jet engine because of the cooler air, and we get better thermodynamic efficiency. So jets are designed for maximum range, as I've already said, while propellers, they are designed for maximum endurance. So this is the mission engine matrix. So this is the basically performance graph for the different engines. So for lower speeds and lower range, we have piston props, as I've already said. Then we get the turboprops. Then we have the turbofan, which is used by the transport aircraft. And then we have the military turbofan, which operate at higher speeds and maybe higher ranges. So engine design comes from the mission, as I've already said. So for turboprop, we have high wing, then we have narrow body, then we have wide body with higher range, and then we have the military turbofan, which gives higher ranges. So this is for the propeller, the different architectures which we take for the aircraft. So for propeller aircraft, we have high aspect wing ratio wing. So for low speed lift coefficient, so low speed we get higher lift. Then we have unswept surfaces, because we don't go at higher speeds here in this case. So we don't need swept surfaces for for limiting the critical Mach. And then we have large diameter propellers, so that we can maximize the airflow going through these propellers. Since propellers actually, as he has already mentioned, it requires more air, like it pushes more air at lower accelerations. So this is for the propeller. So these are some examples of propeller designs. So then we have the jet engine, jet airplanes. So in case of jet airplanes, we need the 35-degree wing sweep, for example, in this case, to remove the critical Mach number effects which comes from compressibility. Then we have high bypass turbofans to manage the intake velocity, and we have supercritical airfoils for transonic cruise. So so we try to maintain the L by D maximum at Mach 0.85 for jets. So these are some different design examples which we have for the different jet airplanes which we have. So first one is the long range wide body. Second one is a business jet here, and the third one is a small commercial small narrow body which we have. Okay, so the next thing is economic reality. So for short range, we have the turboprop, while for the longer ranges, medium to long ranges, we have the jet. So cost per seat mile is lowest for turboprop for for between short to medium ranges, less than 500 miles to 1000 miles. Somewhere in between, we get the minima for cost per seat mile. While in case of turboprop, we get the lowest cost for somewhere at medium to long range, somewhere in between. So these are some future propulsion concepts which people are trying out. So there are open rotor, then you have hybrid electric, then in other case we have the hydrogen, and the last one which is the geared turbofan. So these are different ways people are trying to like use both the benefits of propeller as well as the jet engines. So this is the summary. So propellers are, as we have already discussed many times, so it's the king of low altitude, low speed performance, but it is limited by thrust laps at high altitudes because of density, because of low density, and we have tip Mach limits also, which comes into play for propellers. While in case of jets, they are kings of range or endurance, and they exploit the cold air at high temperatures, which gives them thermodynamic efficiency, and they have to work at high speeds as they move at high altitudes. So this is the final summary. So so in case of propellers, the power comes from moving in large mass of air at small accelerations, while in case of jet, it's basically small mass at higher accelerations. The limiting factor in case of the propeller engines is basically the power at higher altitudes. As we go from higher altitudes, we don't get enough air, so as a result the power which can be supplied is decreased, means sorry, the thrust is decreased. While for jet, the thrust remains constant. The altitude effect, which I have said, it worsens as we move up, while for jet it improves because of thermodynamic efficiency. In case of propeller, we have the tip shock, which is the Mach limit, while in case of jet, in order to counter that, we use swept wings. And propellers are made for endurance or short range, while for jets are made for cruise at long ranges. So this was the presentation. Thank you.
Questions? Good. You wanted to talk about this?
No, that is just what we are showing. Why use turbojet engines at higher altitudes?
Can you go back to the slide in which you had the excess power, which you were talking about?
Is it?
You had marked the excess power shaded. Yeah. Okay. Can you spot the issues with this?
It is excess thrust, not power. Yeah, I mean,
Yeah. That's one. What else?
that is one. I think that is what it is.
Can you look at the legend and find some
Okay.
issues? What do you have in the legend?
True airspeed and force.
Yeah.
It should be thrust available.
It's essentially the difference between what is available and what is required, right?
No. Actually,
Yeah.
it is difference between propeller and jets. So this
Yeah.
is thrust available for a jet. This one, and this is thrust available for propeller.
Available is lesser than.
Available is yeah, and this is the required one. Drag basically.
Okay.
Yes.
So how do you determine the excess power then?
Excess thrust is the region where our the thrust we have is more than the drag which is acting on our aircraft.
Okay.
So if we have excess thrust, we can use it to climb and accelerate.
Okay, but what about the induced drag then?
Induced drag, the induced drag will also act along with it. That is not accounted in this.
Yeah.
So if we really do it right, we should complete the entire drag will be total drag will
Yeah.
be the thrust required, and this will be the thrust available.
No, but I really appreciate just two of you. It's a fairly comprehensive presentation that you have given, covered quite a few different aspects of both jet and propellers, and also piston props and turboprops. Good job.
Thanks.
I think there is a talk by Air Marshal T.D. Joseph at 4 o'clock, the auditorium. So I recommend all of you attend that. Apart from general knowledge of aerospace, I think it's quite relevant to this particular course itself.
Ask it.
So good afternoon, guys. Team BlackBird again. So now we are gonna talk about the influence of atmosphere on why the jet aircraft fly higher and faster than the regular propeller aircraft. So we all know that the usual aircraft fly at an altitude of something around um, commercial aircraft used to fly at 40,000 feet, whereas the fighter aircraft used to fly at a height of 60,000 feet maximum. So not every aircraft could match the level of MiG-25 Foxbat or as the SR-71, as MiG-25 has a record of flying at 1,23,000 feet. So it obviously the atmosphere plays a major role while flying at such condition. So this graphs depicts the variation of the properties which depicts the performance of an aircraft. So that are majorly temperature, speed of sound, density, and pressure. So pressure and density, we know that it monotonically decreases with respect to the altitude, and temperature, but it is not like that. The trend is corresponding to the gradient layer followed by an isothermal layer, again a gradient layer and isothermal layer. So up to a altitude of 11 kilometer, so the temperature of the atmosphere varies with respect to the height, from varying from, to be exact, like following the international standard atmosphere, it is 288.16 at the sea level, whereas at the 11 kilometer mark it is like 216.66 Kelvin. So followed by isothermal layer at 25 kilometer, and this trend follows, and the temperature does not only decreases, it also increases when it crosses the 25 kilometer mark. So yeah, this is a gradient layer which has a lapse rate. So this is this lapse rate. So in order to find a temperature at a particular altitude, we use this equation, and the variation of pressure and density for a gradient layer are given by this equation, where R is the gas constant and lambda is the lapse rate, which is usually 6.5 into 10 power minus 3. So this is the pressure at any altitude corresponding the pressure at sea level, and the density at altitude and sea level. So for the isothermal layer, we all know that the temperature remain constant. So these are the two corresponding equation which gives the changes of pressure and density in the isothermal layer. So these equations we have come across earlier, but we'll do it once again because the topic speaks about why the jet aircraft flies faster and higher than the propeller aircraft. So they have different velocity of operation at which they attain maximum range and maximum endurance. As we saw earlier that the maximum endurance achieved by the propeller-driven aircraft and the jet-driven aircraft are not same. It varies with respect to the kind of propulsion system they use. So we all know that the maximum range and endurance are mostly depend on the CL by CD maximum, CL power 1 by 2 by CD maximum, CL power 3 by 2 by CD maximum. So these are corresponding to different condition which maximize the range and the endurance as well. So these are the derived velocities for that corresponding to where we can achieve the maximum range and endurance. So thank you.
Hello everyone. Today I will tell about the general effect that is found in range and speed due to the effect of altitude. In the like we know the power. The best way to explain the range is through the power required is required and power available. We know the power required is CD by CL 3 by 2 root S and W 3 by 2. From this, you can see the power required is inversely proportional to the root of density. So we can find that the power required for altitude is we can find using this equation. With this equation, we can say that as density decrease with altitude, the power increase with the altitude. Power required increase with the altitude. So we can find the trend that the power increase upward and rightward to as it altitude increases. So we can get the curve which is generally follow as the altitude increases. So like as I told already, like range is a maximum range occurs when the PV by PR by V is minimum. So if we find the tangent, like we will say that the PV by is increasing as the altitude increases. So we can say it tells that the velocity required maximum range is increasing as the, so we can say that like as the velocity increases and time as if we keep it constant, the range increases as uh, range increases as altitude increases for aircraft. This generally shows in both the jet engine and the propeller thing. Next, I will tell about the trend that is followed in the velocity, maximum velocity that the airplane can attain. Like as we can see that the maximum velocity is, can be found by the point of intersection of the power required and power available. So as altitude increases, the we can see the graph comes here, like the point intersection is coming on the left hand side. So we can say that the altitude maximum altitude decreases as the uh, maximum velocity decreases as the altitude increases in the airplane.
So I'll be talking about effect of altitude on a piston engine, how it affects its velocity and its power. So let first, like as an altitude increases, we all know the density will decrease, and the piston engine, like it will use propeller where the thrust is maximum from the mass flow rate. So when density decreases, the mass flow rate will decrease. Thereby, it cannot produce an higher thrust, and also like the tip Mach number, the relative Mach number and tip of a propeller will be higher. So even so, when altitude increases, my density will goes down. Thereby, the speed of sound will also reduce. My tip Mach number effect will become significant at higher altitude. So thereby, I can say that I cannot use propeller. I cannot fly faster with a piston engine, and also like the drop in manifold pressure. So if I have a naturally aspirated engine which uses an ambient pressure, if my manifold pressure is as an altitude increases, the pressure will drop, and also my manifold pressure will drop. And manifold pressure will drop, my the power produced by the engine will also be dropped. So now if I use a supercharger or turbocharger to maintain an manifold pressure of a sea level condition, even with the turbocharger, there is a limitation that even above the critical altitude, I cannot maintain the manifold pressure. Above the critical altitude manifold pressure, again starts to drop, and thereby my power will also reduces. So I just took this graph from the internet. I couldn't fully understand, but I'll explain whatever I understand. So if you look at the second graph, which is on the corner, it's just a brake horsepower versus an altitude. So if you look the general trend that the brake horsepower will decreases with increase in altitude, and also number 28 and 26 represent the manifold pressure in terms of HC. So if I look at the altitude increases, my manifold pressure will also decrease. So by this case, by this sense, I can say my power available will reduce. So if you look at the power required as power available, so as my altitude increases, as my friend rightly pointed out, the power required will goes up, and my power available will starts to drop. So thereby, I can say that I cannot fly my aircraft at so even for optimum range and endurance, I'll have a certain velocity to fly. But my power available starts to decreases. It's give the sense that I cannot fly at a higher altitude and also at a higher speed. Uh, so effect of altitude on the jet engine will be explained by Vishal.
Hi, I'm Vishal, and earlier, yeah, Alvin was explaining how the thrust production system in the propeller aircraft. He mentioned that the majority of the thrust is produced from that mass flow rate component. There, a huge number of huge mass flow rate is accelerated slightly, but in case of the jet, a small mass flow rate is accelerated heavily. So even if with the increase in altitude, the density might decrease, so the mass flow rate might decrease, but it is not as affected by the altitude as the propeller engines. And this is very important parameter, the SFC. How the SFC generally decreases with altitude. I mean, we require a lower SFC for that's we desire a lower SFC. So why does this happen? When as altitude increases, the temperature will decrease. That means the ambient temperature around the engine is decreasing. So with this, the thermal efficiency is increased, so leading to higher SFC. The graph shows how the SFC varies with a Mach number and at various altitude. And we'll try to explain how the range and endurance get affected for jet engines with respect to the brigade equations. At higher altitude, the velocity increases. You might have come across the equation: true velocity is indirectly proportional to square root of specific density. So as the altitude increases, the true airspeed increase, and since the density decreases, the drag decreases with increasing altitude. And just now we explained, with the increased altitude, SFC decreases. Overall, this leads to a with increasing altitude, it leads to a higher range. And in the case of endurance, similarly, it too inversely dependent on the fuel efficiency, which is SFC. So with increasing altitude, the endurance too increase. But with this propulsion, you can ask why we can't keep on increasing our altitude, why we can't have a more velocity. I mean, we do have optimal altitude to operate, optimal velocity. So these are the things that limiting the altitude and the velocities. The lift, when the density decreases, the lift that we can produce decreases, but we need a lift to be equal to at least weight to sustain a flight. And yeah, thrust decreases with the altitude. And there is the coffin corner. Basically, as the altitude increases, the stall speed increases, and the critical Mach number, that is the speed at which at some part of the aircraft the Mach number will be increased. So it will contribute to wave drag. So this point, at this particular altitude, it will both be equal. So this is a safe region to operate. And there is if we increase the velocity too much, the wave drag will increase, and there are structural limitations to dynamic loading too. Yeah. Thank you.
So now I'll be explaining the other atmospheric factors that affect the endurance and range, which has not yet been covered. So the first one is the effect of wind. So we know that wind alters the ground speed, and headwinds increase the range, decrease the range, and tailwinds increase the range. And this can be seen in the graph as well. We see that for a tailwind, the optimal speed for maximum range has decreased, and whereas so it means that at lesser optimal speed we'll be able to achieve the same range as compared to a zero wind. Whereas for the headwind, we see that the optimal speed for maximum range has increased, which means that we require a higher speed for the same range. And comparing it with propeller aircraft and jet aircraft, we know that propeller aircraft's operation speed range for operation is very low. So it's more vulnerable to range variations when it comes to effects of wind, whereas jet aircraft has higher cruise speed, and hence wind has lesser effect on its range. So next is the effect of humidity. Like my friends had already pointed out how density affects the range and endurance, whereas humid air, as we know, has lower density than dry air. And since propeller aircraft, majority of the thrust is generated by the mass flow rate, lesser air density causes lower engine power and lower endurance and range. Whereas in jet engine, it has a relatively minor influence because, as Vishal pointed out, majority of the thrust is generated by the difference in velocity. And when we talk about humidity, we also have to talk about the rain, which increases aerodynamic drag and reduces overall propulsion efficiency in general. So in this graph, we can see that as the specific humidity increases, the thrust fraction, which is the available thrust, also decreases. And it decreases more for piston engine than jet engine. So these graphs were taken from a research paper. So next is the effect of turbulence. So this is another graph that we found from a research paper, which basically said that the we know that the drag coefficient increases with the angle of attack, but as the turbulence intensity increases, if we take for a particular angle of attack, the yes, for more turbulence intensity, the drag coefficient is more. So we can say that turbulence increases drag, and propeller aircraft is more sensitive for this than the jet aircraft. And for both types of aircrafts, both range and endurance decreases due to increase in turbulence. With that, we would like to conclude. Thank you.
Particular last graph, the trend is not very clear, right? In terms of increasing turbulence intensity, whether the drag coefficient really increases or not, seems to be going up and down. Is there an optimal?
Yes, so like for example, 5.21, this is the line.
Correct.
And in
Whereas the lower triangle you see is for 3.42, not for 2.36. The upward pointing triangle.
okay, sir. I think there must be a mix. This is okay. Yes, I disagree.
Right?
But the inference from the research paper itself was mentioned that it basically shows the drag coefficient
Increases.
with the turbulence intensity.
Okay.
We'll look into it.
Sure. Because there are lots of complications involved with turbulence in terms of the separation, etc. It's a little loaded than just simplistic inference. And also, glad you mentioned it's from a research paper, but also if you can just give the source from next time onwards, it'll be good. Yeah. Anybody else? Any questions?
You have told, right, like wind effects. So typically, can you tell for propellers and jets, what is the advantage you're telling, right? Like if you first thing, will wind give same advantage for propellers and jet, or disadvantage if any? And second is, do you know what is the typical wind profiles usually? I mean, where you can get advantage?
Okay,
Which
so
type of altitudes are winds?
well, actually, we didn't look into that unfortunately, but yeah, like I already mentioned, since propeller aircraft operation range for the speed is very low, it is more susceptible to range variations rather than jet aircraft. So we didn't look into the height and what is the optimal height when it affects it.
But in general, like if you look at the range equation, it just depends on the ground speed. So if you look at the range equation, it depends on the ground speed. So based on that, I can say that it is like I couldn't explicitly mention for it will be beneficial for jet and the propeller, but in general, range will increases for the tailwind and it decreases for the headwind. So I'm not sure about how it affects the propeller, how it affects for the propeller and jet engine. So.
Mostly it's associated with the dynamic pressure. That's the reason why equivalent airspeed is much more meaningful in many of these definitions. Thank you.
Thank you.
Yeah, you had.
No problem.
Good.
No question. I have operated piston engines. They were gliders. They were called super demand. They are used in National Defense Academy for the gliding training given by candidates. That is piston propel. So manifold air pressure was basically the manifold pressure for the engine. So manifold pressure is the suction pressure for maintained for fuel supply to engine. It's directly related to two things. One is the air suction and the pressure which we are supplying the fuel to the so it's air fuel ratio for the manifold pressure. And as you go up in the altitude, the manifold pressure has to drop because there is linear. So that's what we do. It's a piston prop engine, so I maintain it.
Yeah.
Thank you.
Thank you. Next team, please.
Good afternoon, everyone. Myself, Navya. Today, we are going to explain how the jet flies higher and faster than propeller in terms of fuel consumption. So, before proceeding with the topic, we have to know what are the fuel metrics and how it affects the performance parameters. I'll be explaining the fuel metrics and performance parameters. So the first one is thrust specific fuel consumption, which is defined as weight of fuel consumed per unit time per unit thrust, and the units are 1 by seconds. And now, when it is in cruise condition, TSFC is relatively constant. And the next one is specific fuel consumption, which is also called as brake specific fuel consumption, which is the amount of fuel consumed per unit time per shaft power. The units are 1 by meter, it will come when we resolve it. And use it with the propeller efficiency to access total system efficiency. And now, how it affects the range and endurance, we will look at it at. When we see the range and endurance, in both the cases, for jet and as well as for the propeller, range and endurance are both are inversely proportional to the thrust specific fuel consumption as well as the SFC. So when fuel consumption increases, range and endurance for both the jet and propeller decreases. And how it affects the altitude, velocity, and the further things will be explained by teammates.
Good afternoon, everyone. I am Tarishi, and I'll be explaining why jet flies faster than props and how fuel consumption is at the crux of it all. As we know, like the jet engine is based on thrust. So, as the formula goes, m dot f is TSFC into thrust, and the thrust doesn't vary with speed. So, the fuel flow also does not vary with speed. So, the jet engine can fly faster to save the fuel. In case of props, like the power required is like d into v, and the drag goes like v square. So the power increases exponentially with increase in velocity. So the fuel consumption also increases in the same way. So prop engines should fly slower in order to save the fuel. Further, Vaishnav will take it forward.
Now coming to why jet flies higher than prop. So first coming to propeller aircraft. So when we start from sea level, SFC initially decreases up to a level that is 10,000 feet. But after that, it started increases, like it increases at higher altitudes. So because air density decreases, so propeller mostly works with higher mass flow rates. Since the air density decreases, the available power also decreases. And to overcome the drag, the power required increases. To maintain the speed or lift, throttle must increase, which leads to higher fuel flow. So as altitude increases, propeller aircraft lose efficiency in thin air, forcing them to fly lower. Coming to jet aircraft, as altitude increases, inlet temperature decreases, which leads to better thermal efficiency, thus having lower TSFC. And as we go higher in the altitude, in the atmosphere, the parasite drag will be lower as air density decreases, which allows higher speeds with less thrust required to overcome drag, improving fuel efficiency and thus reduces fuel flow. Since the temperature is lower, this leads to lower speed of sound. Therefore, for same Mach number, true airspeed will be higher. So this faster speed, there will be faster speed for same fuel burn. So we can say that jets become more fuel efficient with altitude. Generally, prop aircrafts won't be fuel efficient at higher altitudes.
Good afternoon, everyone. I'm Karthik. Let's see how weight comes into the picture with respect to fuel consumption now. Our assumptions are at steady level flight, we have lift is equal to weight and thrust is equal to drag. So now let's increase the weight of the aircraft and see what happens. Increase in weight requires an increase in lift, and increase in lift results in a much higher induced drag, which requires more thrust to move the aircraft. This and one more component being for an aircraft flying at a lower velocity, it will require a higher CL to higher coefficient of lift to sustain its own flight. Both these conditions require an increase in fuel consumption to maintain their specific flight paths. In general, fuel flow rates are proportional to thrust or power required corresponding to jet aircraft or propeller aircraft. Now, this begs the question: why the need to go higher and faster?
it reduces the fuel penalty that the aircraft entails. Going at higher altitudes, the density of air is lower, which results in a lower induced drag, which again reduces the thrust required to drive the aircraft, which again reduces the fuel consumption. This doesn't mean that the weight of jet aircrafts in general are higher than weight of propeller aircrafts. It just means that the jet aircrafts are designed for long range cruise missions, and this entails a typical operation of higher cruise weights and wing loadings that compared to propeller aircrafts. Overall, this minimizes fuel consumption for range.
Thank you, Karthik. Hello, everyone. My name is Anjali Singh. So, where is my slide? Okay. Let's look into architectural effects on fuel consumption. So bypass ratio is calculated as the ratio of mass flow rate of air that bypass the engine to the mass flow rate of the air that passes through the core. So in case of jet aircraft, the mass of airflow that passes through the core is less. So we need less fuel. Fuel to reduce the thrust. So it requires less fuel to achieve the same amount of thrust in case of jet aircraft, because we make a large bypass ratio by making a big fan, massive fan. So if we talked about the type of wings, for jet we have swept wings. Okay, what happen when the jet aircraft flies higher, that Mach number increases. So that Mach number increases will induce that shock waves generation. Because of that induced shock waves, we designed the wings of jet aircraft as a swept. It provides a turn to the flow, which reduces the perpendicular velocity. The velocity component which is perpendicular to the wing, which reduces, which ultimately results in the induced wing drag, wave drag. So it will help in getting low fuel consumption for producing the same amount of thrust. If we talk about the propeller, we have straight wings because propeller will not fly at much higher level. So for that, it has good amount of lift to drag ratio, which will ultimately help in consuming less amount of fuel for producing the same amount of thrust. Now, next, Anjali will continue.
I'm Anjali, baby. So let's look into range and endurance optimization in terms of fuel consumption. So when we are considering range, it is minimizing fuel per unit distance, and for endurance, it will be minimizing fuel per unit time. And we know that SFC for a propeller-driven aircraft is given by weight of fuel per unit power per unit time. So when we are considering weight of fuel per unit time, it is obtained by getting the power required, the minimum power required. So the minimum fuel per unit time is obtained from minimum power required, and we can see that V for maximum endurance corresponds to the minimum power required for a propeller aircraft, as well as for a jet powered aircraft, the minimum thrust will correspond to the V for maximum endurance. So in conclusion, we are looking into what happens between a propeller and a jet aircraft. In terms of optimal altitude, we have seen earlier. In terms of optimal speed, for higher speeds such as speed above 500 mph, there will be a higher fuel consumption for propeller aircrafts when compared to jet aircrafts. And usually, not always, in mission profiles, propeller aircraft will take on the endurance-based missions like loitering, surveillance, etc. And jet aircrafts will be optimized for conquering a high distance, so range-based missions will be there. So propeller sips fuel to stay aloft, as well as jet burns fuel to conquer distance. Now, the limitations of using only fuel consumption as a metric is that it ignores the propulsive efficiency variation with the speed. It does not account for altitude speed coupling, that does not take into effect of Mach contributions. It does not include mission constraints such as time to climb, payload capabilities, or any of that. And it overlooks engine specific efficiency limits like TIT, etc. So that's all for our presentation. Thank you.
Any questions? Any questions? I think one of the things that you mentioned was for the piston prop, 10,000 feet is kind of an optimal. Can you explain the logic behind that? If you can go to that slide. Yeah.
Yes, sir. Usually, most of the propeller aircrafts will float till tropopause or in troposphere. So till 10,000 feet, it is like using like from sea level to 10,000 feet. They perform very well, but after 10,000 feet, the density of the air till 10,000 feet, that will be beneficial for propeller aircrafts. But after that, density will decrease in certain way such that SFC will start increase. So
You've seen some expressions and also curves for the density. There's nothing strange happening at 10,000 feet to make the variation of density with altitude, right? So it's still decreasing.
I have
right?
read somewhere 10,000 feet till that altitude, SFC decreases. So
Yeah,
that's why I
SFC,
mentioned that.
but why? That's the question.
Because of mainly the air density decreases after that altitude significantly. So that is the main reason, I guess.
I think you have to be a little more careful. I think even somebody else, while mentioning drag or power increases or decreases with velocity exponentially, right? One of you mentioned that, which was written also. Just check that. See, the word exponentially is used in the colloquial literature in a very loose way. But for us, exponentially means e power something. That's the rate at which it decreases, right? You have to be a little careful in mentioning that, how it decreases. I think with velocity, when you have a cubic relationship, you were mentioning that it's exponential. It's not, it's cubic, right? Whereas for the density, it is okay. Or the pressure, it is okay. But when you're talking about how drag or power increases or decreases with velocity, you have to be more precise in what you mentioned. Okay. Yeah. Thank you.
Team the Turbulence Squad, and I'm Gaurav Madatta. So today we'll be giving the perspective of why jet aircraft fly higher and faster as compared to the propeller aircraft. And I mean, we have taken a topic. I mean, we have got a topic which actually describes the types of the aircraft. So we'll have to give some idea of, I mean, from some idea from the propulsion and some idea from the aerodynamic design also. So I mean, based on the design or different types of aircraft design, how we can explain that why jets fly higher for a higher range and endurance. So if you look at the most basic equation which describes the propulsion of any flying vehicle, it is nothing but the Newton's second law of motion and the third law of motion, and which is nothing but the momentum principle. And all it says about the equation is that we can generate, I mean, I'm not going to derivation of the equation because all of us are aware of that, but in a nutshell it tells that we can get the forward thrust onto a flying vehicle either by generating a mass flow rate across the vehicle, or by having a huge by having a huge velocity change across the flying vehicle. So this is where the designs basically bifurcate and go into different design concepts. For example, for a propeller-driven, it is basically the m dot which has to be maximized, and we know that m dot is basically a function of the flying altitude, the density, and the area of cross section. So as you can see here, basically the cross section is designed in such a way that they can trap more mass of air and not relying basically on the delta V across the flying vehicle, I mean the engine in this case. Whereas in the turbojets and even in the turbo ramjet engines, we focus mostly on the delta V part instead of taking a m dot as a higher value. And that is the reason why they can fly higher, and that gives two different design concepts. So more onto that, it will be presented by my next team member, Bharat.
Hello everyone, my name is Bharat Kumar, and as we see brigade range equation for the jet, we can clearly see the velocity term coming in the numerator. It shows that range for a jet engine is directly proportional to velocity. As velocity increases, we get more range for the jet aircrafts. And another concept is the thermodynamics effect, also very important in increasing the efficiency of any jet engine. You see, as per the Carnot cycle theory, we should equation says that we should get a lower temperature at numerator and higher temperature at denominator. But for jet engine, higher temperature is limited by the turbine materials. So we try to decrease the temperature in the numerator that we can achieve by achieving the higher altitude, because we get a lower temperature at higher altitudes. and the altitude velocity coupling, which as altitude increases, the density decreases. So we get very less drag in high altitudes, but uh, velocity also increases by the square of the term. So for maximum range, we care for more velocity, which is increasing square of the term, but density also contributes for a lift, but it is very less compared to velocity. That's why we choose higher velocity compared to the density. And another concept is called a coughing corner. uh, in this air becomes very thinner and thinner as altitude increases, but it also increases the stalling speed of any aircraft. So as we go higher in the altitude, as we slow down even a little bit, it becomes stalling of the aircraft. But also another problem arises because of the Mach number. In higher altitudes, for lower speeds only, we get higher Mach numbers, and this also limits us to going higher speeds. At particular altitude for any aircraft, it reaches a point where we can't even speed up or slow down. That is called a coughing corner. And Gaurav will continue.
Here I'll be talking about some examples of propeller-driven aircraft. So first we have MQ-9 Reaper, so which is basically built for providing maximum endurance. So from brigade equation we know that endurance is proportional to CL and propeller efficiency, and propeller efficiency goes down with respect to speed. So to maintain high propeller efficiency, the aircraft flies at low speed around 150 to 200 knots, and to maintain high CL, the aircraft has high aspect ratio around 17.1. So thus the aircraft has high CL and high propeller efficiency, and if it flies at maximum endurance condition, CL to the power 3 by 2 by CD max, so it can provide maximum endurance around 27 hours. So at the right hand side we have another propeller-driven aircraft, so which is actually built for providing maximum range, and it flies at very high speed around 0.8 Mach number. So at that high speed, to maintain high propeller efficiency, the aircraft has some special arrangement and orientation in their propeller blades. So first it has contra rotating blades, which actually recover the energy, and it also has sweep angle in the propeller blades. So because of that, the propeller efficiency goes up, and the aircraft also has two counter rotating propeller in between. So because of that, the air flows over the root of the wing, for that CL goes up. So the aircraft has high CL and high propeller efficiency, and because of that, if the aircraft flies at maximum range condition, that is CL by CD max, so it can provide maximum range around 15,000 km. So in the next part, examples of jet propelled aircraft will be talked by others.
Hello, myself Adarsh. First, we'll talk about the Lockheed U2, which is also known as Dragon Lady. This is aircraft operate at 7,000 feet altitude. But there is a problem at that altitude, the density of air, which almost very negligible. So to give the sufficient lift, either we can increase velocity or platform area. But there is a limitation in velocity at it cannot increase beyond a critical Mach number, which will be very detrimental to its structure. So velocity is also very our limitation. So here platform area is very much high to generate the lift. Now we'll talk about the Boeing 787 Dreamliner. This aircraft flew at 45,000 feet altitude. As you can see from the range of jet is directly proportional to V by Ct and L by D. Its velocity is very high, around 490 knots, or we can say Mach 0.85 at 45,000 altitude. There is also a problem that it cannot go above 45,000 altitude because lift-induced drag will increase, and cannot go below 45,000 altitude, which results in increase in parasite drag. And to increase L by D, here we have raked wingtip. Without increasing the weight of the aircraft, it will increase L by D ratio. So due to this, L by D increase and range is also increased. Now we'll talk about next Concorde. As Concorde is the very fast aircraft. It has a terrible aerodynamics. It has L by D ratios is around 7. typically the L by D ratio required around 20 to 50. So to increase the range, we are only dependent on V by CT. So it travels around 2 Mach number, and at this 2 Mach number, due to very high ram effect, the efficiency, thermal efficiency also increases, which results in decrease in CT value, as CT is thrust specific fuel consumption. So if combustion efficiency increase, the fuel consumption will decrease. So at flowing at 2 Mach number, V by CT will increase. So we can get high range even though L by D is low. So we can say that the range of any jet engine is directly proportional to its velocity. Now Yash will continue further.
So starting with the failure case 1, the compressibility valve. So XF844H is made for, they are trying to mimic the propeller aircraft to fly like a turbojet aircraft. So basically issue ये था कि जब यहाँ पे इनका प्रोपेलर का जो स्पीड था, उन्होंने जब भी टेस्टिंग किया था तब उनका प्रोपेलर का स्पीड 1.18 मार्क तक जा रहा था, जिसकी वजह से वहाँ पे शॉक्स जनरेट हो रहे, प्लस नॉइज लेवल इतना ज़्यादा था कि जिसकी वजह से जब वो फ्लाई कर रहा था तब भी 10 माइल्स दूर भी अगर बंदा खड़ा रहेगा तब भी उनको साउंड सुनाई दे रहा था। इसकी वजह से उसका सिर्फ 10 आवर्स ही फ्लाई पीरियड हुआ था, उसके बाद ये प्रोजेक्ट को बंद कर दिया गया था। सेकेंड केस है द थर्मोडायनामिक मिसमैच, द कैप्रोनी। सो जो भी हम सब बोलते हैं कि 1940 में टर्बोजेट स्टार्ट हुआ था, बट 1940 में उसके पहले और एक चीज़ हुआ था जो है कैप्रोनी। कैप्रोनी का सीन ये था कि उन्होंने यूज़ किया था मोटर जेट। मोटर जेट क्या होता है कि आपका दे यूज़ पिस्टन इंजन। पिस्टन इंजन आपका ड्राइव करेगा कंप्रेसर को, और कंप्रेसर सब्सिक्वेंटली कंप्रेस करके हम कंबशन में फ्यूल डाल के डायरेक्टली उसको एग्जॉस्ट कर देते थे। बट सबसे बड़ा डिसएडवांटेज ये रहता है कि आप फॉर्मूला 1/T कोल्ड बाई टी हॉट। सो जैसे वो लोअर एल्टीट्यूड पे होता है वहाँ पे उसको टी कोल्ड उतना मिलता ही नहीं, जिसके वो लोअर एफिशिएंसी रहता है। सेकंड है आपका पिस्टन इंजन इतना आरपीएम जनरेट नहीं कर पाता, जिसकी वजह से कंप्रेशर उतना कंप्रेस नहीं करता है। और थर्ड है वो कोई भी टाइप का नोजल नहीं यूज़ करता है, सिर्फ वो उसका जो एग्जॉस्ट है वो सिर्फ डाल देता था बाहर। इसकी वजह से उतना उसमें थ्रस्ट जनरेट नहीं हो पा रहा था, प्लस ऑलरेडी ये बहुत ही बल्कियर था तो इसलिए वेट भी बहुत ज़्यादा इंक्रीज कर दिया था। थर्ड है ज्योमेट्रिक ब्लेंडर, ग्रूमैन का है। ग्रूमैन में सब स्टार्टिंग जब हुआ था तब सब लोग स्वैप बैक टाइप के एयरक्राफ्ट यूज़ करते हैं, बट इन्होंने प्रपोज किया था स्वैप फॉरवर्ड टाइप का। स्वैप फॉरवर्ड टाइप में सबसे बड़ा एडवांटेज यही रहता है कि आपका जो फ्लो है वो इनवर्ड आएगा, ना कि आउटवर्ड जाएगा। इनवर्ड आएगा तो उसकी वजह से क्या होगा कि आपका जो विंग टिप है वो विंग टिप स्टॉल होने से बच जाएगा। बट इसका सबसे बड़ा डिसएडवांटेज ये रहता है क्योंकि विंग टिप स्टॉल नहीं होता है, बट फ्लेक्सिबिलिटी की वजह से आपका विंग टिप के ऊपर लिफ्ट का वेक्टर ऊपर की साइड आएगा, बट आपका सीजी पीछे की साइड लोकेट रहता है, जिसकी वजह से एक ट्विस्टिंग मोमेंट क्रिएट करेगा जो ऑलरेडी आपका एंगल ऑफ अटैक बढ़ा देता है। तो इसके लिए उनके पास जो इलेक्ट्रॉनिक कमांड रहता था वो 40 या 50 के उतना पर सेकंड उनको कमांड देना पड़ता है उसको काउंटर एक्ट करने के लिए, जिसकी वजह से सेफ्टी रीजन की वजह से अगर थोड़ा भी कंट्रोल फेलियर हो जाएगा इसमें, ऑटोमेटिक कंट्रोल फेलियर, सो वहीं पे ही आपका एयरक्राफ्ट क्रैश हो जाएगा। एंड द लास्ट वन इज द इनफाइनाइट एंड्योरेंस सोल्वर, नासा X57। नासा वैसे बहुत ही एम्बिग्यूअस प्रोजेक्ट करते हैं। सो वन ऑफ द प्रोजेक्ट ये था कि हम लोग ऐसा कोई एयरक्राफ्ट बनाए कि जिससे मेरे को मैक्सिमम एंड्योरेंस भी मिल जाए और मेरा सबसे लिमिटेड फ्यूल यूज़ करना पड़े। सो उन्होंने क्या किया, 14 प्रोपेलर यूज़ किए, 12 छोटे वाले और 2 बड़े वाले यूज़ किए। सो कंसेप्ट ये था कि स्टार्टिंग के जो 12 है वो जब मैं टेक ऑफ करूँगा तब वो हायर लिफ्ट जनरेट करेगा, और जब क्रूज पे पहुंच जाएगा तब 12 के 12 प्रोपेलर बंद हो जाएगा और सिर्फ मेरे जो 2 बड़े वाले प्रोपेलर है उसी से मैं थ्रस्ट जनरेट करूँगा। बट इसका सबसे बड़ा डिसएडवांटेज ये था क्योंकि ये इलेक्ट्रिक प्रोपेलर था। हमको ऑलरेडी पता है कि आपका कोई भी जेट फ्यूल लेता हो तो उसका 43 मेगा जूल पर केजी मेरे को जनरेट करना रहता है। अगर मैं लिथियम आयन भी लेता हूँ तो उसका 1 मेगा जूल पर केजी करना, तो उसके लिए मेरे को उतने लिथियम आयन बैटरीज लगाने पड़ेंगे जो ऑलरेडी यूज होने के बाद भी वो एज अ डेड वेट ही यूज होगा। सो मेरा एयरक्राफ्ट का वेट कम ही नहीं होगा। सो 2023 में उन्होंने उनका जीवीटी टेस्ट एंड वो किया, बट वो कभी भी सर्टिफिकेशन के लिए नहीं गए, क्योंकि इसमें सेफ्टी जो उनका थर्मल लोडिंग कूलिंग का उनके पास इतना बड़ा आंसर नहीं था कि जिससे वो पायलट को बचा सके। इसके लिए वो लोग उन्होंने 2023 में ये प्रोग्राम बंद कर दिया।
So hello. So I won't be taking much of your time as Yash has already taken mine too. So let's start. So we can see first edge case. This is it refers to ramjets as the velocity engine, because in ramjets mostly the speed is not a result of the thrust, but actually it is also the source of the thrust. And next, the model high bypass. In high bypass turbofans, we can see it can have bypass ratio of up to 10:1. And the main function of the turbofans is to displace a high chunk of mass across the fan to generate a higher thrust. And the bypass produces almost 90% of the thrust, and the core produces 10%. And here is the hybrid paradox. Actually, we see that the helicopters can hover for how much time it wants. It means that it has an infinite loiter, and while airplanes have a high range. So to have both in a single system, we have this V22 Osprey, where the airframe transform between these two configurations. And the last, talking about the 6th gen adaptive cycle. In this, what happens, the fighter aircraft can produce a high thrust, and the bombers have to perform efficiently. So this gave to a need of variable bypass ratio. So there is a variable thrust stream. The thrust stream you can see in the green, the variable bypass, where what we do is that when we want high maneuverability or high speeds, then we close this third stream, and when we want a high efficiency, then we open this third stream. Now, Somik would like to continue further.
Hello everyone, I'm Shomik. So as you can see in the top right corner, we have the flight regimes, and we can see that different aircrafts are built for different flight regimes. So it's obviously not a one design for all regimes. And then we come to the second part, the top right bottom, which gives the crux of all the discussions done by my teammates. So we can see here so basically propeller airplanes are optimized for endurance, and the only limitation they face is that supersonic tip speeds, and their thrust range equation is also power based. As a result, it is they cannot go for longer range with their velocity, whereas in the jet range equation we have the range proportional to the velocity. As a result, for high velocity they can cover high range, and the limitations for jet aircrafts are generally the thermal limits, which melt their airframe, and also for the jet aircraft to maximize the range, they need to go at a higher altitude where they have less dense air to that resist their motion. So it is very clear from the quote given below: if you want to stay up long, fly slow and low, and if you want to go far, you must fly fast and high. And finally, as the limitation for the jet aircraft was given the thermal limits, so there's a proposal for an hypersonic 7-gen transport aircrafts which can be cooled by regenerative cooling. That is the very fundamental theory in cryogenic rocket engines. So, and here also we will be using the cryogenic hydrogen as fuel. So, giving to my next fellow teammate.
Good afternoon all, myself Nirav Gupta. So, in order to conclude all this analysis we done, there are three distinct key design considerations which come out to be very significant during any flight journey or during any flight. First is the endurance parameter, and as we seen earlier in the MQ9, the MQ9 uses very high aspect ratio wing in order to maximize the endurance. We have seen that earlier also. And chevron nozzles for maximum range, which uses 787 uses these kind of nozzles in order to maximize the range. And then we have the inlet, sharp inlet spike, sharp inlet used for high maneuverability, raw speed for aircrafts like SR-71. So where from these design considerations come? These are nothing but when we break it down to pieces, these are some raw basic mathematical equations which from which equations these design considerations have come, and we are basically eventually we are seeing the physical manifestation of those mathematical equations when we put those equations into our design process. So when we conclude this, we are concluding that the design of aircraft is not just a physical design, but a lot of mathematics is put behind any design, behind any mission, and this is our conclusion that it is not just to overcome physics. We design aircraft to submit the equation to solve particular kind of range equation which depends on the mission needs. For example, if we need a high range, we need to fly at high Mach number and all. So yeah, that is the conclusion.
Anybody any questions? You?
I just wanted to say, the question was exactly asked for if there has been in the world somebody in the propeller aircraft regime, I mean in the propeller aircraft domain, somebody has thought of range being the parameter, they must have designed an aircraft. If it were jet aircraft, somebody must have designed a jet aircraft. In the same way, endurance being the main parameter, some aircraft must have been there for endurance alone. Some aircraft must have been there for range alone. So typically those pickups were actually asked for. More or less, partially you did your efforts. You forgot hail. High altitude, long endurance.
Sir, because the other team has already covered that part. That's why we are not.
Was not covered.
No, sir. We are the last contender. The other contenders already covered hail part. That's why we are not.
No comment. No arguments. If not, you will bring up hail and say there is an aircraft which does many things.
Okay, thank you very much. It's good to have a lot of case studies, and also in terms of the variety that you brought about, because in the short time that is allocated to you to bring out certain concepts, it's always good to have a varied case studies. So congratulations. And also, I think not for you, you can head back. I have a few visitors from Boeing, so I have to leave early, so we'll not have the remaining presentations. We'll have it on Monday.
People have already left.
Yeah, no, they mentioned. Thank you.
Good afternoon, sir. We are Team garuḍā and myself, 𝥂Jet Misra. Sir, earlier we have seen why jet has to, means a jet can fly higher as well as faster than a propeller. Today, today's topic is why a jet has to fly higher and faster for carrying more weight. Earlier we had seen that it can. Today we will see why it should do for more weight. Okay, as we all know, sir, that in aerodynamics, the force balance will be between lift and weight and drag and thrust. Okay, so now coming to weight, if we need to carry more weight, we need to generate more lift. And for generating lift, we have 4 parameters, that is density, velocity, span of means wing area, as well as CL. We know that CL has a limitation of maxima, as well as for a given envelope, S also will be limited or will be constant. So we have 2 parameters, that is velocity as well as density. And from this equation, we can see that the effect of velocity, because it is squared, will be more than the density. So for carrying more weight, aircraft has to fly higher, faster. Okay, now for flying faster, the issue is of drag. As you fly faster, you need to surpass more drag, and in turn, you have to burn more fuel. Okay, so obviously the range and endurance will be limited. But jet aircraft does one thing, that with higher velocity also it can fly to higher altitude, thus reducing the density and compensating the drag on that. Okay, so using a jet aircraft, we can fly higher as well as faster. Further, my teammates will discuss.
So thank you. So I will explain the question based on the optimization of drag. So let's start with the brigade range equation. So we have R is equals to V by C L by D L and W by WF. So for the maximum range, we need V to be higher and L by D should be maximum. So L by D should be will be maximum if we get the minimum drag. So induced drag and parasite drag will contribute to the total drag. So induced drag is directly proportional to the square of weight and square of the velocity. So if our velocity is higher, then our drag will be minimum. So, and in general, jet aircraft is heavier than the propeller aircraft. So now come to the parasitic drag. So parasitic drag is directly proportional to the square of velocity. So if we increase the velocity, our parasite drag will increase. So we have to decrease the parasite drag. So parasite drag is directly proportional to the density as well. So which decreases with the altitude. So we can say that a jet aircraft fly higher and faster than the propeller aircraft for maximum range and endurance. Thank you. I would like to invite Rohan.
Now let's look at the propulsion efficiency. Before that, let's see what is actually a propulsive efficiency. It is nothing but a thrust to engine power ratio. And when we solve it mathematically, we get a relation and we also have one more relation which is connected to total or overall efficiency. So the basic idea is that if the propulsive efficiency is high, then we can say that total or overall efficiency is also high. And intuitively, what does it mean is that if efficiency is high, then there is a less loss of energy. So that less loss of energy can be converted to achieve long range or high endurance. So that is why this is important to learn. And now let's see for subsonic region in propeller at low Mach numbers. In propeller, what happens is this VE is almost equal to V infinity. That's why propulsive efficiency is high in propeller. And when we come to turbofan, the V exhaust velocity for turbojet is very, very high. So that's why this efficiency is very low. And at certain Mach number, after that, the role is reversed. Because when we look at the propeller, as we increase the radius, V is equals to omega r. There is also one more component, this. So at the tip, there can be a supersonic region or sonic region due to which there is a high wave drag. So endurance and range decreases. But what happens in turbofan? Basically, what happens is this V infinity, as high Mach number is there, this V infinity is increased. So therefore, the efficiency is increased. And how does it affect our altitude and everything? Let's look at lift is equals to weight. And so from here, we get V is equals to under root 2W upon rho SCL. So from here, we can see that at high Mach number, that is high velocity. We need weight high, or we can also conclude that density is low at high altitude, which means. And for low Mach number, which is propeller, we can say as velocity is increased, it is generally used in low weight, and density can also be increased. So it is at low altitude, and turbofan is at high altitude. I would like to call.
Okay, so our fundamental topic is why it fly higher and why with a higher velocity. And we have to somewhere connect it with why does it has higher weight? Because we know jet aircraft are pretty much with heavier than with propeller aircraft. And all these three things are pretty much connected because the first question is why does it fly at higher altitude? The basic question is because it can. And why it can? Because the propeller aircraft, the rate of climb depends on power available minus power required. Similarly, for the jet, it is thrust available minus thrust required. Now, the relation is quite funny because For the propeller, PA is directly proportional to density. But when you compare the thrust for the jet, it is directly proportional to density raised to the power something between 0.7 to 0.8. So when you decrease the density of an aircraft, because when we go higher in altitude, density decreases, the PA reach its limit first before the TA. So propeller aircraft give up first, and the jet aircraft give up later. So because of that, the jet aircraft can reach at higher altitude, and at higher altitude density is less. So when density is less, for the same drag and for the same lift, you need a higher velocity, and that's a good thing. But because of that, the jet aircraft need more fuel. The jet aircraft need to harness a more combustion at a higher temperature. So the engine need to be lashed with superior alloys, which will cost us weight. And moreover, the structural load which will experience by the jet aircraft is much more higher than the propeller aircraft. Therefore, the weight of an overall jet aircraft is supposed to be much more higher than the propeller aircraft, and that's what we can see. And the question arises why the propeller aircraft give up before the jet aircraft is we can see that the propeller aircraft depends on its blade, and those blades kind of choke before the engine in the jet aircraft because those blades are moving at a pretty high speed. And at higher Mach number, if they reach a higher Mach number, the possibility of them choking is much more higher than the jet aircraft. Moving on to Nitin.
Myself, Nitin Jaiswal. I'll be trying to revisit the range parameter for the two jet and the propeller aircrafts. So, as it has already been discussed that the jet aircraft tries to fly at a faster speed and at a higher altitude, and the range typically depends on the three parameters primarily, which are efficiency and the aerodynamic characteristics and the amount of fuel it will carry. With respect to the jet aircraft, efficiency will certainly be higher as explained earlier because of the high exhaust velocity. The aerodynamics, that is the L/D ratio, will be better because of the low parasitic drag, and the amount of fuel that it will carry will be more because of its higher weight and higher fuel tank capacities. So thereby giving them a higher range with respect to the propeller aircraft. Further, Sanket will continue.
Hello sir, my name is Sanket, and I will tell you that why propellers are best suited for endurance or like long time in in surveillance, and jet is suited for longer range. As we have seen with the help of propulsion efficiency that our propeller based aircraft have a higher propulsion efficiency because their delta V is low but their m dot is high, while jets have a lower m dot and their delta V is very much high. So inherently a jet has to fly much faster than the propeller aircraft. Now, if I try to increase the speed of the propeller aircraft, then what happens is that compressibility effects or the different types of losses start to take place at the tip of the engine. So we have to inherently fly it at low speed. And what low speed? The speed at which the drag is minimum. So because it is flying at a drag minimum condition, the power usage is low. Because the power usage is low, the fuel consumption is low, and hence I can spend much more time in the air. While in case of jets, what happens is that jet has to fly inherently faster. So if I fly it at a minimum drag condition for point A to B, it will spend much more time in air. So my energy consumption, which will be equal to drag multiplied by the power or the velocity multiplied by time, because the time factor is much higher, it will spend a lot of fuel or overcoming the drag even though the drag is low. But if I increase the velocity, as we have seen in the Brigade's equation, that even though that we fly it at 1.32 times, like 32% higher than what is the minimum drag speed, what happens is that my time in air start to decrease faster, and hence I can spend less fuel for flying the same distance and in the same time. This is why I prefer jet propelled jet for a longer range, and because it is a longer range, the weight increases. Why? Because I have to carry more fuel to cover the distance. While at the same time, my propeller-based aircraft, because it is spending less fuel, it can fly for much longer time, but also it can be lightweight in nature. Thank you. I would like to call
myself Ashish Raman. So let's have a look at the Brigade range equation. As you can see, I will just repeat this. I think already it is covered a lot. The velocity term is not there in the prop. So increasing the velocity doesn't increase the range and endurance specifically for a propeller aircraft, whereas for a jet, the range equation is given by this, where you can see there is explicitly a velocity term there. So mathematically, if we look, it says that if we go with a higher velocity, our range increases. Now let's have a look at the wing structure design of a conventional jet aircraft and a turboprop aircraft. For a turboprop aircraft, the wing will usually be a high aspect ratio and it will be thinner to avoid the drag at low speeds. Whereas for a jet aircraft, because it will be flying at high speeds, you need a swept wing design, and the swept wing design allows us to have a thicker wing root. This thicker wing root basically helps us in having a larger fuel ratio because you can put more fuel in that. And so you can see the jet wins twice. For velocity increase, you get a better range, and this Wi by Wf, which is nothing but the fuel fraction. So it is winning twice. You basically you get with more fuel, you can get more range, and the velocity increase also helps this. Now the topic of this assignment was why do jets fly higher and faster? And for us, specifically it was why explain with the help of the weight or the loading. So we went and we thought, what happens if we reduce the weight? The weight is not there. So can we go high and fast? So this is a Helios aircraft, NASA Helios. So this is a HAL aircraft, a high altitude, long endurance. So you can see here the wing loading is much less, which is less than 5 kilogram per meter square. Usually for a jet aircraft, it will be around 780 kilogram per meter square. Its cruise speed is only 25 knots and flies at 60,000 feet. So this aircraft was actually paper thin. You can say it was like a tissue paper design. So what happened was, because it was so thin, it was so structurally weak, because you can't increase the weight. So it crashed. And this proves that if you have to put but there was no utility of this. I mean, in terms of payload carrying capacity, you don't have you can't carry payload, because the moment you put the payload, weight comes. Weight, for that maintaining the weight, you need to make it structurally rigid, and the mass comes. So this proves that you don't jets don't fly fast because we choose to fly higher and faster. The weight of the payload exiles us to that regime. Thank you.
I don't think I have much to explain, but I'll conclude. To answer the question why jets fly higher and faster than propeller aircraft and has more in terms of weight, in the perspective of weight. So basically, as we've seen, lift requires velocity or density or wingspan. So if we have more weight, we have to produce more lift. If we want to produce more lift, we have to either fly at high velocity or we should have a very large wing. And we all know having a very large wing has its own limitations. It will have more drag and it will also increase the weight, and there is some optimality. So considering, let's say, the wing area as a constraint, so the only option is to increase payload. We have to fly faster. So if you fly faster, so now we come to propeller versus jet. So propellers, they have their own limitations. As already mentioned, they can't fly faster than some speed because their tip velocity will be very high, and it will have wave drag in the tip region, and the efficiency of the propeller will be very less, and the fuel consumed will be very high. And so since we want to fly faster, the only option is jet. So if you want to fly faster in jet, so there is one more penalty. The drag will be higher if the jet is flying at low altitude. So if you go to higher altitude, let's say 30,000 or 40,000 feet, so it is a sweet spot for the jet. That is, we have rho into v square. So that term, it is optimized condition. So you can fly at high velocity as well, and the drags will be less. So your fuel burnt, the amount of fuel burnt will be less. So to conclude, the propeller-driven aircrafts are like king of endurance. They can have higher endurance because propeller engines, they have highest propulsive efficiency, and their fuel consumption is very less. And for the jets, as I mentioned, it can fly faster. It has to fly higher, but the problem is the fuel consumption is very high. But the thing is, since it is flying faster, it might not be able to, let's say, loiter or stay in air at very longer time, but it can cover more distance. It can travel further. So that's why. So for, let's say, if you want to carry high payload and if you want to cover a long distance, you have to design a jet aircraft, which is something like 747 or 787. But if you want a high endurance and let's say the range is limited, you can design, or you can have a propeller-driven aircraft, something like MQ-9, as already mentioned. It will have very long endurance. You can do a lot of surveillance, and so that's what. So since the weight increases, you have to move into the jet region, and you have to fly faster and higher. Thank you. Sri Charan.
Who's close to?
Are there any questions from the audience? The subtopic for you was weight or load. What did you understand by load in this context? Because it came through implicitly in a lot of things, but I want to understand explicitly. Weight, of course, it came across very clearly. What did you understand by the subtopic weight/load?
It was actually two schools of thought. We have considered as a payload.
Okay.
Which we carry.
Good. Yeah. Okay. Okay. Did any of you come up separately regarding the payload weight or the payload fraction of the overall gross weight? What is the impact of that in terms of the choice of the engine and also the range and the endurance?
Yeah, actually we have done some studies, sir. It's like range or endurance, it will go something like this, sir. For jet, it will be having a bigger envelope, that is this entire area. For propeller, it will be smaller than this envelope. If I...
What is the y-axis there?
Payload, sir.
Oh.
This is payload versus range or endurance. Okay. Not to scale. Okay, just to...
Same behavior.
Qualitatively, it will be like this.
Okay, why is it constant initially?
Initially, sir, we are this is being taken as same constant and being limited by maximum takeoff load. Okay, payload is same, but maximum takeoff load is different. Based on that, fuel loading will be different.
Okay. Where does the penalty of the engine weight come into picture here? Of all the fractions that you're talking about, I could see you talked about fuel fraction, some of you have mentioned, and also the overall weight. Still, it's not coming out very clearly in terms of the payload fraction, because the payload fraction is going to be a leftover from your empty weight fraction, your fuel weight fraction, etc. Right? Coming to that, how exactly is that going to determine the choice of your engine? Yes, I understand from a range endurance point of view, speed, altitude point of view, many of those things were covered in your slides.
So the maximum takeoff weight is nothing but all the payload fractions multiplied. Let's say the structural weight fraction, let's say the fuel weight fraction, electronics, and then the payload weight fraction. So if the payload fraction is high, so all of it will be implicitly high. So it's an implicit relation. So if you want to carry more payload, let's say your aircraft should have like higher wingspan, because landing and takeoff you have to still do at low speeds. It's not like you can land at a very high speed. So you will have, it's limited by stall characteristics. So the wing area will anyway high. But so when you have a higher wing area, your structural weight will increase. So it's an implicit relation. So if you want to carry more payload, as we already mentioned, you will have higher weight. The total weight of the aircraft will be higher. So since the total aircraft weight is higher, you have to fly faster to have a, let's say, optimal endurance and range, basically range. So you want to fly faster, you have to go with the jet engine, because you can't fly faster with propeller engines. So you can, this is a classic example of, you take a cargo aircraft, which is a C-17 Globemaster, and there is a A400M, which is a British Airbus aircraft. Those two look very similar. Both are cargo aircrafts, one has a jet engine, one has a propeller engine. But the philosophy is different. One is a strategic lift aircraft which can carry for long distance. It can go from USA to UAE. But this is like, the cost is higher, the fuel consumption there is higher. But in A400M, it can also lift a substantially good payload, but it can't travel longer distance. It has a range limitation, so it's like this.
Yeah. See, many of these things you're aware of, but it's not coming out very clearly in the presentation, which is what I would like you to bring out in the future presentations. Because there were lots of things that you could have probably cut down on, which were already covered or will be covered by the other teams in terms of the effects of the altitude, etc., for example. While you can still touch upon it for completeness sake, but I think the focus should be more on your own subtopic, because from your explanations, it was very clear that you are aware of what is involved, but it's not coming out quite explicitly in the presentation. Okay. But like the slide designs, I think you use Perplexity and stuff. Or
Notebook.
Notebook. Okay. In terms of the slide designs, number of words per slide, etc., it's come down since your previous presentations, which I like. So that the focus is, I can listen to you, I can see you eye to eye and hear what you're saying rather than keep reading what is written on that line by line, sentence after sentence, sometimes paragraphs after paragraphs. So that's a good change, and I would like you to continue on that trajectory. Yeah, please.
Now we have, last semester we went to Propulsion course, right? So there is a operating speed or basically a design speed about which the engine performs the best. So do you design the, engine for the aircraft or the vice versa?
It goes actually both ways. Some manufacturers, so based on their analysis or market, they'll order the engines for the, let's say, engine manufacturer, let's say GE or Airbus, GE or Rolls-Royce.
For example, there is an engine which works well at a speed say V, but when you design your aircraft, and now the things are showing that it needs a speed. For example, you made it for a range, our endurance, for example. Now it requires different speeds. So how will you do that then?
So you'll not choose that engine. We'll look for other optimal engine. If there is nothing available, then you have to go with that and you have to change your design itself.
The mission requirements will
drive the engine design. Yeah. So basically, to take an example, LCA is being designed for GE F404. You can't fit another engine with that for that.
It was not designed for GE.
But it was designed for Kaveri.
Yeah,
but then it was transformed to this. And now the upcoming AMCA, it is being designed for, let's say, F404 as well as.
So the mission roles decide the choice of the.
Exactly.
Anjapa, you have any questions? No, thank you. Next team, please.
Because the topic is already known. Last time we were discussing about range and endurance maximization. Today it is why you go up for jet and go down for propeller, and with respect to L/D ratio. So actually L/D ratio, if we see the L/D max, because in range last time we had presented Breguet equation. So we will first start with that because that was our older topic, so we have connection with that. And then we'll try to relate L/D, but most of it is not exactly explicitly coming as L/D in Breguet equation. It is in power, in some powers of L, CL or CD. And L/D max as such per se doesn't vary much with altitude, to be honest. But there are other ways where it affects, so that we will cover. So yeah, so Bhavika will.
Good afternoon, myself Bhavika, and I'll be taking you towards a closer look at L/D. So what is L/D? L/D is, in layman terms, it's how much lift is generated per unit drag, which is the aerodynamic efficiency. So when we see an aircraft, we obviously want to maximize the aerodynamic efficiency. That is, we have to minimize the drag. So when we take the drag polar, I think this graph has been, we have been accustomed and very familiar to this drag polar since it's in every presentation. But from this we know that at low velocities we have a high CL. That means the total drag, which is this curve, is dominated by the drag due to the lift, which is the CL term. So, and when there is a high velocity, the total drag is dominated by the zero lift drag component. So there exists a velocity at which this zero lift drag actually compensates the drag due to the lift, which is the point of D minimum, and which gives us the L/D max. When we look at, when we take a closer look at the graph of thrust required to velocity, we see that this dashed line refers to the D minimum. So in a steady level flight, where the engine throttle is at the thrust required minimum or the thrust required, and then there is a perturbation, suppose a horizontal gust. So we see that the velocity decreases, which momentarily increases the drag, but the engine throttle is untouched. So that means momentarily the drag is increased against the thrust. So the aircraft velocity decreases and goes to unstable positions.
But on the right side of it, the opposite happens. So the aircraft velocity decreases, but it stays stable. I would like to hand over to the next person. Thank you.
Okay, we are revisiting Breguet equation because last time we presented there, so first thing we wanted was to start look there. We looked there in the first thing. So if you see the L by D max, so already Bhavika covered that the maximum occurs when induced drag and parasitic drag is equal, and when you do that, you will get this relation CD naught into K. So CD naught mostly is dependent on Reynolds number, but if we say with respect to altitude, it would not vary much. And as such, L by D max, the value won't vary with respect to altitude. So to be honest, L by D, if you see the explicit effect, it would not have any effect if you just see the formulas. Because if that is not varying with altitude, you would not want to change anything. But if you see the propeller efficiency, that okay, so we'll start with Breguet equation. So we have a range we had derived in the last presentation, the range for both propeller and jet. So if you see, there is an L by D explicitly coming, or the fraction of CL by CD, and then there is a density term in the denominator once you put the velocity for maximal range, and here there is an efficiency. So when you increase the altitude, your propeller efficiency decreases because of the m dot effect, because you need to have a higher mass flow rate, and you need to have a high velocity, and you'll not and your tip also has issues. So overall, if you fly at the lower altitude, the efficiency will be higher, and hence reduces. Oh, this I have written wrongly. It is increases reduces altitude. For jet, density is coming explicitly in range equations. So with that, anyway, we can say even if CL by CD characteristics we keep same, saying that we keep the velocity and other things constant. CL by CD, so there is a CL by CD characteristic and there is a density characteristic. So if you reduce the density, directly you will gain in range. And plus the efficiency of engine is also higher, which was explained in the previous groups, that the colder air will have a higher efficiency. Then with respect to endurance also, we can see for directly jet, there is an L by D coming, which is not varying much, but the CT value, which is lower for higher altitude, so that way also for jets higher altitude flying is benefiting. And for lower altitude, again the density term is coming, so if density is higher, you will get a higher endurance. So overall for propeller, endurance and range both are beneficial if you go to a lower altitude, and for jets it is better if you go to a higher altitude, because propeller, one thing already, most of the things are covered already, that tip speed is an issue. So and propeller is driven by m dot rather than wRight, so m dot also will be higher for a lower altitude. Then we have just shown here typical L by D for different aircrafts. So we can see that for jet, this doesn't show anything of maximum L by D. For each it will be different, but just to show that jets will have a little higher L by D, and prop aircraft will have 15 to around 15 L by D. It doesn't relate anything here, but just for completeness. Then yeah, this is the wRight, maximum V for jet and prop for maximum endurance and maximum range. So there also we just wanted to show that how density explicitly comes. So if you want to go to a lower, higher altitude, you have to increase velocity for the same weight. And the tip speed, anyway, we have seen that if you increase altitude, you need to have a higher velocity for the same weight. And there the Mach limit comes. And if you go to a higher Mach number, your D suddenly increases. There's a drag divergence curve, which we know that like approximately a lower Mach number, drag will not change, CD will not change very much. But as soon as you go to a transonic or higher Mach number region, the drag will suddenly shoot up. So if you just see the subsonic L by D, it will be almost constant, not changing with altitude. But D as such will increase, and then all of a sudden you will have a sudden drop in L by D for propellers. So their L by Ds will fall significantly, which will affect the performance. So we need to have a maximum altitude range for propeller.
Good afternoon. So I'm Michael. So as told by Survey that the drag would increase as the tip reaches the sonic speed range. So you can see because of that, if a compressibility effect, the thrust generated by the propeller degrades very sharply as it reaches the sonic region. So, but the thrust required would be as per the equation because it has to cancel the drag. So we can see because of the degradation of the propeller performance, propeller thrust, the intersection of the two is basically at a lower limit, but for the jet it is at a higher limit. So because of this particular phenomena of the propeller engines, the velocity, the optimum velocity at which it will fly would actually be lesser than the jet velocity. So it basically this sort of connects to how the propulsion actually works for each category of the engine. So this is the thrust available and the thrust required, and respectively we have the power as well for both jet and the propeller. So next will be done by you.
Okay, so in general there are two flight plans that aircrafts generally follow, and if we look at the first one where we maintain constant CL and speed, we get the Breguet range equation for that. And our goal here is to keep the aircraft at the maximum root CL by CD configuration. If this gives us an optimal velocity of 32% higher than that of the minimum drag velocity. And if we look at the lift equation, if we maintain constant CL and V, that means as the weight reduces and we need to reduce the lift, the aircraft has to climb higher into an ideal cruise climb. This would result in lowering of parasitic and induced drag together. But in a constant altitude and speed configuration, if we have to reduce the lift along with the weight to maintain a level flight, we have to reduce the angle of attack. This would result in the reduction of CL, which in turn would result in the reduction from the slipping off from the root CL by CD max configuration. Thus, the instantaneous range would keep decreasing throughout the cruise. This would result in a reduced induced drag, but the parasitic drag would stay more or less the constant, and hence would require more thrust than the ideal cruise climb phase. As we can see, the drop in thrust is much higher in the former than the latter. So aircraft generally used a stepped cruise climb to stay as close as possible to the maximum root CL by CD configuration that maximizes the range. Now, for the propellers, the range equation from the Breguet range equation, we see that we just need to maximize the lift to drag ratio, and hence the optimal velocity that we get is equal to the minimum drag velocity. So there are two options for the propellers to maintain maximum range, either to increase the velocity at either to decrease the velocity at the constant altitude, or to keep the same speed but keep gaining the height. And there's a altitude restriction because of the efficiency of the propeller blades as discussed by Surbhi. And what that graph that we saw in many presentations earlier, that's a graph for Gulfstream 4 aircraft flying at a constant height and weight configuration. So what that conveys is that if we fly the same airframe in a propeller versus jet engine configuration, what we see is that the jet configuration has more velocity and endurance than the corresponding propeller counterparts, as the root CL by CD peaks at a higher velocity than the lower ones. Third, what we see is that the airframe design goals are different for a prop and for a jet, because we need to maximize root CL by CD max for the jet, while for props we need to maximize just the maximum lift to drag ratio. Therefore, this results in a higher aspect ratio long wings for the propeller aircrafts, and the goal is to make the wetted area minimum for the prop aircrafts. But for the jet aircrafts, there's a velocity term in the factor to be minimized, and hence it has to be made capable to fly at higher velocities, resulting in a swept back wings such that the velocity encountered by the wings is just a perpendicular component of the actual velocity at which the jets are flying. And the further will be discussed by Pragya.
So how high can you fly? This is the situation of coffin corner, in which the pilot has a very minimal range for operating speed. So what happens at higher altitudes when there is a stalling condition? We have L is equals to half rho CL V square. So this density decreases when we are at a higher altitude. So the speed has to increase. So the stall speed increases. And for this max speed, we have at high altitudes again, temperature reduces. So due to less temperature, the sonic speed reduces, and which leads to a reduction in this speed. So because of this reason, this is the only operating range the pilot has. So why this happens? When we are flying at a very high level, and if the aircraft is heavy, then again high temperature if the air is hot due to turbulence or updrafts, then autopilot issues where the pilot can't control this, and during step climbs. So this is it. Next, Harika will cover.
So I'll just summarize whatever we have discussed. So L/D ratio, we know that it defines aerodynamic efficiency, and for steady level flight, thrust is equal to drag, and drag is inverse proportional to L/D ratio, and L/D ratio is maximum when induced and parasite drag are balanced, and it is inversely proportional to thrust, and so for propeller aircrafts, the L/D ratio is the limit of L/D ratio is low, and for jet it is high, and Mach also for propellers there is a strong restriction for the Mach number. So because of compressibility of blade tip velocity, and for jet it is weak, so that's why it can reach high Mach values, and that's why it can't reach high altitudes, and jet can reach high altitudes because it doesn't have compressibility problems, because it is designed for compressible flows, and that is how jets can reach higher altitude and high speeds. So, and thank you.
Any questions from the audience?
They mentioned something about the L/D ratios for different aircraft. Can you revisit that slide?
Which one?
So you mentioned L/D for light prop aircraft and turboprops are lesser than the turbojet and it's a long range jets. Is that always true?
Of what? Like
Is that always true? Can't you design a, let's say, light prop aircraft with a higher L/D ratio?
No, you typical. Okay. One thing is jet has to go to a higher altitude, typically, and you would require either CL. There you will require a CL higher in general. So should jet ka CL should be a little higher than the. I don't think so. It is.
CD
I don't think so. It is.
CD कम
हाँ?
CD कम
हाँ, CD कम CL ज़्यादा.
to save you on a weight to save.
वैसे नहीं altitude. So I don't think so. It is a typical number. I don't think so. Any. If you have any comments, you can tell.
You can design a light prop aircraft with the very highest CLS because
You can, but airframe design will dictate that, na, how much L/D. This is a typical number. So, like typically what aircrafts are.
Sure.
Mic. हाँ.
Regarding that, as we go higher, we know that Propellers we have lower LYT. For jet aircraft, we have higher LYT, right? Then this is the wing span.
Actually, L by D will not change very much because you are going that time either you are when you are going to a lower density, then you are going faster. Approximate because you want to dwell at L by D max sort of thing, and that is not very much changing with altitude. That depends majorly on flow physics. So unless Mach is drastically changing and your flow is
Regarding like supersonic aircraft, once we go for like supersonic aircraft, like onboard or something like fighters, and the LYT ratio is decreases, right? We use the wing. What is the reason here?
what is
What is the reason here? Why do we design the wings in supersonic aircraft?
supersonic? You will have a very high drag, right? Like you can't meaning.
So
Or
supersonic
Mach
has,
wave, whatever. So you will be.
You have wave drag in the supersonic regime, right?
So you will design according to that.
Reduce because of that.
There is a drastic increase in drag if you.
Yeah, but you need to have the same L to balance the weight at that point.
We have ambient fighting and drag, right? One more question I would ask regarding that. What is it? Office point. Please show that.
Again.
So it's like a impact by popping corner rises high temperature on air. I think as you go above the altitude, the air should cool down. Why is the temperature of air increasing?
There is a mistake in the slide.
Temperature is large.
नहीं वो mistake है नहीं it is written wrong. It's wrong. It's lower temperature. I explained it like this.
I have one question. So for a maximum range, and if you have a supersonic aircraft, so how many Mach numbers are there for a higher range?
Mach numbers?
Yes. So if you have Mach number less than 1, is there any range that you will get a higher range, and above Mach number 1 you will get a higher?
The range of Mach number.
Range and Mach number depends.
It's like you have two velocities where you can get same maximum range.
वो इसके बाद
Below Mach number 1 and above Mach number 1. So
what I'm trying to ask is there a relation between the Mach number and the range?
Okay.
There's a relation between Mach number and velocity. So
right.
This whatever V is shown.
Yes, sort of better. We have two Mach number where you get the same higher range. One is lower than Mach number 1 and one for higher than Mach number 1.
So if you solve the range equation, you get two velocities. One velocity corresponds to a subsonic and other corresponds to supersonic. Is it true or not?
Yeah.
Something like this.
Huh?
Right? Like, are you saying that there are 2 points of intersection, so you have 2 velocities? Okay.
But if okay. How much would be constituent power?
No, but this graph is not for the range. It's only for thrust or power available and required. So the thing is, the first point of intersection may not be actually achievable because you cannot fly that low at such low velocities.
But I have seen that the supersonic aircraft has
two Mach numbers is for maximum range.
Okay, we'll look into that.
That we mentioned when we go supersonic, they actually reduce the size of the wings to compensate for the drag.
मतलब swept back sort of. So effectively you are reducing. Huh?
But we maintain the same LYD, right? So if we are reducing the size of the wings, how we are maintaining the same LYD?
So angle of attack.
For example, like onboard has like onboard is half the wing span of a normal airline, but it still flies at the same altitude. So it should maintain the same LYD.
So what you can do is, you have higher drag because of the velocity and because of the wave drag, right? But if you want to maintain the same man, you have to basically, increase the CL by increasing the angle of attack, because CL is function of alpha, right? If you increase the alpha, you'll get the more CL. Of course, you'll have a little bit more D also, but you can maintain, you can fly at a particular angle, which will have the same alpha.
नहीं तो B ना effectively, right?
हाँ.
You wanted higher B, that's why you designed that, right? I mean.
हाँ नहीं ठीक है सही बात.
And the thing is like we actually make it smooth cut, like going for takeoff.
हाँ. That's what we said. Okay.
What is the question of delta?
He's like, sir, supersonic mein you'll need for wave drag you'll need delta wing.
No, for speed drag.
So that is what.
Then what is the question?
There is no question, sir. That is comment.
Comment.
Okay.
So just want to hear what he said.
Okay, done. Yeah, thank you.
There was not much, to be honest, much content on explicitly L by D. So, like, if we were not able to do justice to the topic properly, I mean, there is a lot of scope. So, for that.
Yeah, it was reasonably good. Okay, we're done for the class. There's nobody else, right? Presenting. We're done. Oh yeah, yeah. Yes.
Yeah. Like, can you explain, sir, what is
Please,
that?
yeah.
What actually happens? So
Sure.
Can you explain? I am asking. Just to clear the doubt.
No, what exactly is?
The doubt is, so I showed the Navy aircrafts, they landed with the high sink rate and there are two planes. And the Air Force aircraft, they do the front because they have a plane. And Sir gave some points that it's not, this is that they land like that every time. So I wanted to like, get
No,
back.
so we were also talking after that. So essentially, there are multiple angles to this problem.
Yeah.
See, we are trying to mix up too many things.